This
Right.
conference will now be recorded.
So welcome everyone to another OCP Tab session. This is call number 77. Today we have David Maitling from Xeris, right?
That's correct.
Okay,
Yes.
Xeris. So David is the CEO of Xeris, a startup building a global timing service to expand beyond GPS. David has 3 decades of experience in space industry, including Hughes Space and Comms, Orbital, Maxar, and Bridgecom. David has a Bachelor of Science in Aeronautical Engineering from Cal Poly SLO and a Master of Science in Aeronautics and Astronautics from Stanford University and an MBA from MIT Sloan School of Management. So with no further ado, David, the floor is yours.
Thank you. Thank you, Ahmad. It's my pleasure to be presenting here in front of the Time Appliances Project. We've been participating and listening in, learning a lot from the members here at the Time Appliances Project. So it's wonderful to actually present and talk about what we're doing at Xeris, which is quantum time transfer. So the advertisement all the way first, like Ahmad said, we are a startup, fairly early stage, a bit over 4 years old, around commercializing technology that was invented and patented by my co-founder, Dr. James Troop. He figured out a very novel way of using entangled photons for very secure and very accurate time transfer. So we made pretty good progress since then. You know, we've gotten some Air Force, NASA, SBIRs, SBIRs, but we're now at that point where we want to launch our system on a satellite and provide a resilient timing backbone to augment timing from GPS and potentially open the door for new applications. So without further ado, let me talk. So the intent, Ahmad, I gave a presentation, workshop on synchronization and timing systems this past March. It was really our first opportunity to talk about this technology that's relatively new. So if you haven't heard of it, you'd be forgiven for that. You know, PTP and other time transfer methods have been around for a while. This is new, and only recently have we decided to bring this out to the commercial market. So the intent today is to break a presentation that I feel is a little simplistic for this audience here. We got some very talented experts in, you know, in clocks and time transfer. But really, I want to make a presentation that is something we can show or something that like can work with the general audience, the layman, your grandparents, so to speak. So I'm going to start with a little bit of background, a little boring for some of you on this call here, but it helps segue into why quantum time transfer is unique, how it works, and the potential applications that can be unlocked with it. And the last thing I'll say, before I move from my commercial break, is we rely on partnerships to develop the system. You'll see it's a fairly ambitious mission we have, and so we really want to work with the companies that are active and part of the Time Appliances Project. So really look forward to hearing back and getting direct feedback from people and working with you. So let's start with the very basics. Let's start with this idea that you have a clock. It's a master clock for the globe, for the world, and you want to distribute that time over large distances, over global scales. Well, what you do is you start with an RF carrier, a very stable single frequency RF carrier that can be broadcast by satellite. Satellite is the most efficient way to move, to distribute communications over long distances as well as time. So you start with a carrier, a wavelength, and you basically modulate it. You basically can just change the phase 180 degrees, and that change in phase, sorry, it keeps jumping ahead of me. That change in phase becomes kind of the marker for a timestamp. I kind of liken it to, you know, back in the olden days where they had, you know, the signals, you know, the time balls and things like that they used back in the 1700s. That change in the phase is your marker. It's your, hey, Mark, it's 8 a.m. You know. So that's kind of how you would set that up. And then to make it even more precise, you would add in kind of assign each of those phase differences a code. So basically 0 degrees is a 1, minus 180 degrees is -1. And the nice thing about that then is you can not only get kind of like a repeating irregular pattern, but also you get the ability to modulate a signal on there, transmit information with the same signal that you're using to transfer time. So, spoiler, I'm talking about GPS. Again, apologies for this. I guess it decides to move on its own. So when you start with the GPS code, the satellite will broadcast at just changing the modulation, the phase as it goes back and forth. And then you on the ground will have a receiver. And that receiver will be used to, that receiver then will have that same code tied to its own clock. And that clock then can be referenced to the clock that you get from the satellite. And then that offset becomes the difference in the time between the satellite and the ground. Now, you also get the benefit too now, like I said, you can now add information on top of that. So what GPS has done, what other GNSS systems have done is they create the carrier, they create this repeating code, and this code kind of changes or varies depending on the carrier and some other things. And then you put on a nav signal on top of that that actually has useful information about the satellite. And that includes the satellite you're receiving from, the position and time of, well, the position of the satellite, date and time, the status of the satellite, not that you care as a person on the ground, like I don't care how well the satellite's working, but it can be used to help weight the information to get your position in time, as well as some overall information. And then that satellite would be then used to broadcast to you. You'd use the difference, like I said, in the offset of the phase changes to calculate your distance or the time. For enterprise timing applications, you don't care about the distance of the satellite, you just care about getting a very good time reference. But most mobile users, they want to know their position and time. So they basically resolve the distance between them and the satellite. And then if you want to know your position and time, you need to have multiple satellites in view, because you know the distance of multiple satellites, you know the position of all the satellites. You can triangulate your position. And then you have the code. The code has to be available for the receivers to use. One of those interesting stats, there's almost as many GPS receivers on the world today as there are human beings. The majority of them are in your phones. And all those receivers, they're kind of open source, use a code that is published by the US government. And there you have it. There you have GPS. GPS is the gold standard for time distribution around the world, position and time distribution, frankly. It's maintained by the US Space Force. It's coming up on the 50-year anniversary. If you guys didn't know it, Labor Day 1973 is where the initial group got together and developed it. If you are interested in history, it's fascinating. Just read some of these accounts by Dr. Brad Parkinson, where he talks about how it was formed. It was really originally designed as lighthouses in the sky with the goal of, getting munitions through the same door twice, kind of thing. And GPS has evolved since then. Now it's got a few different signals, and it's been working great. However, there are limitations that come with GPS and just any type of RF time transfer. But one of which is the very obvious, which they talk about in every conference I go to, and everybody knows this very well, is just the ability, the weak RF signal is trivially easy to jam. You can go online, it's illegal in the United States, but you could go online and buy a $10 GPS jammer that plugs into your cigarette thing. And definitely it's become more in the news recently with Russia invasion of Ukraine, just how easy or trivial it is for it to be jammed. And that's just a function of the fact that it's a weak signal. You have a receiver, unless you have a very high-end receiver, it's hard for it to just be overwhelmed by a jammer, even a small one that's nearby. The other one is, and because of that, you get outages, and those outages could be due to malicious jamming, it could be due to atmospheric effects, it could be due to a wide range of things. The US government is starting to monitor and track outages, but in Europe, they did a fairly comprehensive survey, and they reported over 100,000 reported outages per year under a GNSS program there, and that was just in Europe alone. And that was just what was reported, and then they did a whole data set to say, okay, how much of that was malicious, how much of that was due to other factors. It's a fascinating report. And of course, the just limitations in the accuracy. So the accuracy comes as a problem because essentially it's a rack and stack. So everybody here is familiar with time budgets. Every piece part of that limits the accuracy, and part of the limitation that you get with RF versus optical or quantum, which I'll talk about next, is the fact that it's you get an RF signal, it penetrates clouds in the atmosphere fairly well, but it's also it gets impacted by dispersion effects, it's impacted by multipath, and it's just kind of the broad spectrum of that kind of creates a little bit of loss, kind of defining that edge of the phase change. Now, the other thing is just basically security. So security, I feel like is kind of it's been a big deal for the US military or for military agencies forever, but for the commercial groups, particularly the commercial groups on this call, security really hasn't been a concern or an issue. But I think there are some applications or some use cases today that are going to make security more important. And security is really one of the truly beneficial things you get with a quantum time transfer system. Now you can improve the performance. There's a number of ways to improve the performance. And the most obvious way is just multiple signals. So GPS has 3 signals, L1, L2, and the recently added L5. But if you are, again, very fixated or focused on having a stable time reference for your network, you would want to have a multiple signals opportunity. And fortunately for you, there's a lot of new entrants on new kind of global navigation satellite systems. Here's a nice chart that just got published by the European Union. Some of them are aligned, some of them aren't. And there's also, again, we've seen the presentations from other very good quality systems that are being launched, basically kind of space startups similar to ours that are providing newer signals that can be added into your network. And some of those companies are looking at stronger signals. And the way you get stronger signals is essentially you've got a satellite in a medium orbit that's about 12,000 kilometers up there away from you. Bring the source of the signal closer, have it put them in low Earth orbit. Now, if you know anything about orbits, that's an easy way to get a stronger signal, but then you need more satellites for coverage. Just fundamentally, higher you are, the more you can cover. So it doesn't scale too well. The other option is a signal over fixed beacons like a cell tower, and that's some work that's being developed right now. Now, on the security side of things, you could also go with encryption. And this is something that the US government does with the signal on the GPS satellites, particularly the newer satellites that are coming on board. But you need a special receiver to use it, and it's only available to the US military. I don't know if they're making that available for civilian use or not. The other thing is, and I kind of like to highlight this too, is two-way time transfer rather than one-way time transfer. GPS, because it has the broadcast, the modulated information onto the carrier, you don't need an RF two-way time transfer, you just need a one. Two-way though will make the hardware more complex, but will give you better precision and will allow you to at least have some steps in there where you can authenticate the signal. So it'll give you better accuracy and better security. Now, the other thing is, and I'll talk about this in the next couple of charts, is optical and quantum time transfer. Optical is fundamentally just, it's basically, optical and quantum are basically just different flavors of the same type of system. With an optical time transfer, you're taking a laser, you're taking advantage of very stable ultra-fast pulsed lasers, and you're using that as your leading edge. You can kind of change it with a kind of pseudo-random code, or what we've seen on orbit with systems that are being launched or been demonstrated on orbit is they essentially just use the on-off keying or other optical communication method that they're using to do some time transfer demonstrations. Now, optical time transfer has already been out there. It's been demonstrated on fiber networks, White Rabbit, and so forth. But it hasn't been used much for satellite-based time distribution. And I got a few theories why, but yeah. Now, quantum is brand new. The fundamental difference here, if you can visualize this, is I'm not using the change in phase or the leading edge of a pulse to do the mark. I'm using actual individual photons. I'm leveraging technology that's been developed for other applications that creates a pair of entangled photons. And these photons are created from one photon and they're born at the same time. And then subsequent photons are also have that really tight time correlation at the time of creation. And I'm measuring one at my transmitter, kind of clock A, and sending the other one down to the ground to clock B. And those individual photons, it's not a wave of photons that's hitting you with an RF signal or an optical signal. It's individual photons that create a discrete click on a single photon detector. And that opens the door really to some better resolution of the time and potentially much, much better precision. So going back to optical time transfer, I want to highlight a few areas where they have been launched and demonstrated on orbit. And there's actually a few missions coming up where they're actually trying to do a bit more, because again, for some of these scientific missions, RF-based time transfer just isn't accurate enough for kind of future applications, or for some of these scientific applications, I should say. And a lot of these systems are taking advantage of satellite laser ranging and optical communication systems that have been developed for satellites. Satellite laser ranging has been around for a while. It's actually been around since the 60s and 70s. And it sounds like that would be like, oh, somewhat complicated and ahead of the curve. But really, essentially what they're doing is they're adding retroreflectors. In some cases, they cover satellites with retroreflectors, so like flying disco balls. And then the laser just bounces it off the ground. So you're basically using that to get a very accurate range measurement using kind of like the optical link. And then of course the other one is the big shift over to optical communications. My background in satellites, my whole career, the majority of my career, everything has been RF communications off satellites. But about a decade or so ago, optical communications started being implemented on science projects, including the JASON-2 satellite, the LLCD, which is the lunar laser communication demonstration, and another kind of number of kind of these demonstrations, because optical communications just fundamentally gives you much, much higher bandwidth. And some of those projects, they started like, well, let's use that kind of beacon, because you do need a beacon for optical communications, optical time transfer, and quantum time transfer. Modulate the beacon, we can use that for time transfer. So optical communications is starting to go on satellites. Definitely we, as our company, as we look at launching this and providing a time distribution system, we're actually kind of looking at the idea of offering optical plus quantum, kind of similar to kind of different carriers in our RF system, kind of muxing them together. Now, I'd be remiss if I didn't talk about optical frequency comb. If NIST hasn't given a presentation on this, Ahmad, you need to get on that, because they've done some very impressive things with optical frequency comb over free space links. And they're looking actually to launch an optical frequency comb demonstration on some future satellites that have not yet been funded. They're very impressive. They're getting femtosecond level accuracy. On paper, quantum time transfer, we can get sub-picosecond into the femtosecond realm, but as a company, we're just, why? It doesn't feel like anybody wants sub-picosecond. So the optical frequency comb is impressive, but it's not, it kind of solves a problem that isn't interesting for us as a company. But NIST, Dr. Newberry, Dr. Sinclair, they've done some very impressive things, and I do believe that they're working toward launching it. One limitation though is frequency comb. They got some new, I think, microresonator technology that will work on orbit, but otherwise it's going to be a little difficult to qualify that, space qualify that and have it work on orbit. So quantum time transfer, you know, like I mentioned, hey, look, we're using tangled photons and Alice and Bob, and we're measuring them and doing that cross correlation to figure out the offset between the two clocks. But it also has some very impressive security applications that make sense when you understand some foundational things of quantum mechanics. So indulge me for a little bit, you know, as you go back to your high school quantum physics class. One of the key things that we're leveraging is this magical, very hard to understand aspect of superposition of quantum states in a small object, a particle. This has been very well outlined by the original 100 years ago by the Schrödinger and the wave function equation. It essentially says that behind the door, before you can observe this particle, it's in a superposition of quantum states, and you can specify or talk about those states with the wave function, but you can't observe it or measure it directly, because when you do observe it, you measure it, it collapses into one state. And that's a foundation for the Copenhagen interpretation that says, fundamentally, I'm paraphrasing here, you're never really going to be able to open that door and see what's in there. You can have the wave function, you know what's happening. There have been a ton of experiments to prove that, but you'll never truly know the quantum state until you observe it. And this is, some people have called this a measurement problem. It's also spawned other theories or ideas like, you know, the many worlds interpretation and the pilot wave theory. I'm not going to get into it because I'm not smart enough. But just understand that not being able to look behind the door is a foundation for some of the security, because now you have, it spawns a no cloning theorem, which says, look, I can measure this once, but I'm not going to know everything that was happening behind that door, so I can't retransmit it perfectly. I can't clone that quantum state once I observe it once. The other one is entanglement. Everybody talks about entanglement. Everybody's got some big ideas about it. We're definitely leveraging entangled photons for the security aspect of it. You know, entanglement is basically when two particles are together, they hang out a bit, they get entangled until they're maybe potentially maximally entangled in one of different areas, and then they share the same properties. No matter how far apart those two entangled particles are, once you measure one, the other one collapses instantaneously into the kind of orthogonal state or kind of complementary state through the magic, that spooky action at a distance. Einstein wrote a famous paper, a thought experiment on it that actually kind of came up with this idea of entanglement, but only in the sense that he didn't like that aspect of it. But last year's Nobel Prize winners were three gentlemen that proved this with experiments. Well, what they proved was Bell's theorem. John Bell, brilliant mathematician in the 60s, looked at this and said, look, how do we know there's not anything hidden going on there that's creating that entanglement? So he wrote Bell's theorem, and then the three gentlemen who won it were ones that created very clever experiments that proved it. And they call what they call the CHSH inequality, or Bell's inequality. So with entanglement, now we're actually creating entangled particles. And one of the amazing, so through this kind of this manipulation, the creation of, you know, and manipulation of quantum properties, where it was spawned a whole series of what they called the third quantum revolution. The second quantum revolution was really creating lasers and MRIs and atomic clocks, but now we're actually creating and manipulating quantum properties, including entanglement. And one of those applications, everybody's very famous, is quantum computing. This is what everybody's very excited about, because quantum computers, use entanglement of multiple particles or particles to create qubits, or actually superposition within them to create qubits. Quantum computing gets all the funding, but we are not quantum computing. Just very clear about that. The other application is quantum sensing. Quantum sensing is actually very interesting, very fascinating because of the things it unlocks. It's using the quantum properties of particles for very sensitive inertial reference units. Atomic clocks fall into that category of quantum sensing, but also there's some very impressive things going on that are very sensitive. RF, gravity gradient, and magnetic field measurements. And so within the Time Appliance project, we're all time here, I understand that, but it's worth following some of these companies and what they're doing, because these are going to be revolutionary in the future, especially I think about like what these sensitive RF sensors and using this quantum gravity gradient to know your position incredibly accurately. Disruptive is what I'm going to say, but it's kind of like quantum computing. There's still a number of years, potentially decades away from rolling out. Now we're in the camp of quantum communications. The quantum communications is entangled photons, or photons basically. So they're kind of flying qubits is a way to think of them. And we're leveraging hardware that's been developed for other applications, and particularly quantum key distribution. Quantum key distribution was fundamentally, particularly entanglement type quantum key distribution, was invented in papers in 1991. Basically saying, hey, look, we got this ability now to create photons that are entangled. We got detectors that can detect them. These photons share information. I can use that to transmit. They're random, fundamentally random, but once you measure it, you get a 0 or 1 at both parties. And I could use that to create a random string of bits that become an encryption key, and that encryption key could be used to encrypt the data between the two parties. So quantum key distribution, we're really just kind of drafting on the hardware that was developed for QKD applications. Again, they've been around now for a while. They're rolling out networks, particularly if you look at adding quantum time transfer to the networks. We're kind of hard targeting networks that are already putting in QKD systems. So it's already off the shelf. You can buy this hardware. You can install in your network tomorrow if you wanted to. Now, this is where I always do before I really get into the meat of quantum time transfer. Again, to be clear, we're not quantum computing. We're not clocks. We're not sensors. We are not entangled clocks. Everybody kind of confuses us with one of those things, thinking we're launching, there have been experiments done with kind of creating local entanglement of clocks. Again, we're focused on creating that long distance time transfer necessary for the applications that you all work with day in and day out. So how does it work? Okay, so we start with a laser. Same laser you would use for optical communication systems, except that we're not pulsing the laser. We're basically dialing down the power of a blue laser until you get a steady stream, a stream of blue photons. And those blue photons then are converted into pairs of red photons that are entangled. It's half the energy, so kind of twice the wavelength. So blue converting to red, and then those would go to single photon detectors. And this technology has been around, like I said, it's been developed for QKD applications. Again, you're starting with a fairly straightforward blue seed laser. Goes through some nonlinear crystals. Those nonlinear crystals will spontaneously convert individual blue photons into pairs of red photons. They're correlated at this point, but they go through some more nonlinear crystals, and kind of in that process of hanging out together, they get entangled. So we've developed our system with correlated pairs, and we're working with entangled pairs, because entanglement is what gives you security. So this hardware has been developed for quantum key distribution applications. You got a source of entangled photons at the transmitter Alice, in cryptography terms. Creates the two pairs of photons. One is measured at Alice, single photon detector. The photon goes in there. There is a rudimentary timestamp applied to that, because You do need to, compare the photons you're getting at Alice to the photons you get at Bob. The other photon goes to Bob, and because that photon is entangled with Alice's photon, the man in the middle, the eavesdropper, Eve, can't measure the photon for Bob. It can't measure it and retransmit it because it breaks the no cloning theorem. The quantum properties are broken. And QKD, because it's about creating this random, these encryption keys between Alice and Bob, have to be very secure. A lot more secure than distributing time from Alice to Bob. So there have been security proofs. There have been a lot of development toward creating a very secure QKD systems. And again, we're drafting on that as a lot of that technology. So the breakthrough my co-founder had, Dr. Troupa said, look, Alice and Bob have clocks. Bob wants to synchronize his clock to Alice's. Let's use that exact same kind of system. And it requires a bit of a modification of hardware, but mostly what it requires is a change to the methodology. So you could have that almost exact same setup. In fact, when we originally wrote the paper and patented this, demonstrated this in a quantum lab, we started with a QKD setup. And this worked, we got down to roughly 50 picosecond level accuracy with a system that was not designed or optimized for quantum time transfer. And fundamentally, we can go with nearly an identical QKD setup if the distance between Alice and Bob is known or static. Now, once you start adding some dynamicism in there, some unknowns between that Alice and Bob, well, then we go to two-way quantum time transfer. It essentially works the way two-way optical or RF time transfer work, which is now the distance between Alice and Bob can be a variable that drops out as you're sending, the photons in both directions. So it doubles the hardware, but it adds a level of precision, and also then, particularly for a space-based system, it's nice not having to worry about, trying to figure out the distance between Alice and Bob. Now, unlike optical or RF time transfer, these photons are fundamentally random. The randomness is, and by random, I mean it is random, provably random with a Bell's inequality test. Quantum processes are fundamentally random. They're not pseudo-random. They're not flipping a coin random. They're truly random. But randomness creates security, but it also means that we need an exchange of information over a classical communication channel. So we have to add an optical or RF comm link between them to exchange information. We can't modulate the information on the RF or optical carrier. So, yeah. The protocol works basically as you'd imagine it. Alice creates entangled photons. Well, they each create entangled photons. They send them to each other. They have a set of detectors at each side, detect them. The photon hits the detector, and it's stamped with a timestamper, electronic timestamper, that's tied to the clock at Alice and Bob. So I'm time stamping it. I get the arrival of photons. I'm stamping it with my clock. My clock could be off by an hour. Who cares? You're time stamping it. You collect the data. When we built this, we've only really needed to get a few hundred photons exchanged between Alice and Bob in a static link with normal background noise to get picosecond level accuracy. So we only really need a small window. And of course, what you want to try to do is get a few hundred photons within a very small time bin. So if I'm getting 1 million photons exchanged between Alice and Bob per second, I'll take a very thin slice of that. Because again, if I can get a few hundred photons in a picosecond bin, then I can resolve the clock, even as those clocks are drifting within a very tight bin. And then all the magic that we're doing, really the fundamental thing that we're working as a company where our trade secret, the proprietary piece is in the algorithm part right there. So we're spending a lot of time really refining that algorithm in our system. So We're not really focusing on the hardware, though we do have some work to do on the hardware side of things, but we're spending a lot of time getting the algorithm. So a real-time time transfer with only a second of linkage. So, okay, all right, now there's RF time transfer, like again, we've seen all these and other things. In other presentations here at Time Appliances project. So one of the biggest advantages, okay, we can get 10 picosecond level accuracy, potentially we can get sub-picosecond level accuracy. I've heard that fundamental physics says we can get roughly 40 femtoseconds, but who wants 40 femtoseconds? Really, I think the value we're creating is the fact that we're thwarting that man in the middle. We're thwarting that eavesdropper. We're leveraging what's been done on QKD to prevent jamming and prevent spoofing. And we think that has some value, but we're kind of sussing out some of that right now. Now, the obvious one is, and these are kind of the things we've identified. Now, what's not on the list here is military and DoD applications. We've gotten funding from Air Force and NASA and some other government agencies who are interested in this for resilient PNT applications. But for the commercial and kind of non-government or scientific missions, it kind of breaks down into enterprise network timing. Again, providing that time reference for networks, for data centers. We're not going to necessarily provide the time distribution within the data center, but we can have a receiver on the roof of your data center, on top of your base station, on top of your system that links to our satellite. Our satellite is providing only time, so we only need one satellite to provide continental hemisphere-wide time distribution. We believe this will work over on a geo orbit, so it could be a fixed point in the sky. Realistically, that receiver is going to pick up our signal as well as other multiple signals opportunities, so it'll still get the GPS, maybe Galileo or other signals. But when you sync to our system, that is going to be a calibration for the other RF signals, as well as creating that time reference that you know is trusted. It's only coming from our satellite. So enterprise timing is important. Obviously, network security. We kind of glossed over this a little bit, but as the photons are sent between Alice and Bob, if you have a man in the middle that's trying to create a artificial time delay, that's trying to measure it and kind of retransmit it, the quantum properties are broken. And because the signal is fundamentally random, it's random as it's created, the eavesdropper can't sit there over to the side with their own CA code and transmit their own version of it. You know, hey, I'll block the signal from Alice and I'll transmit my own to Bob. So it's got some provable security. Now, it's also interesting for network security because not just kind of this application, but we recently responded to a DARPA quantum augmented network call where they look at quantum properties across classical optical networks as providing that physical layer to detect network intrusions. There's still some development going on in that arena, but there is a vision of the future where a classical network, an optical network, can use these quantum effects to detect any intrusion within the network. Which brings me to the next thing, which is trusted time. Again, this ability to verify that the time is coming from our satellite and our satellite alone could be the backbone for, say, a trusted timestamp for security exchanges, you know, MiFID II and some of these other ones that are coming up. We kind of, actually, I got a bit of interesting, the Deutsche Börse presentation a few weeks ago was very fascinating about how groups are starting to create a product for a trusted authenticated time. The other one is, this is very interesting too, is time of flight. Time of flight is something that we can take advantage with in time of flight. So in theory, you have two clocks that are synchronized. You got an RF or an optical link between them. You can use that kind of change the time of flight it takes for that signal to hit you. And okay, there you go, there's your time of flight. But think about now, we're measuring individual photons and the time of flight of individual photons. And also consider too that there are dispersion effects in the atmosphere, through fiber, through any medium that's not a vacuum. And all of a sudden now you can see a world where you can use those dispersion effects and we can actually measure, hey, this photon at 780 nanometers is traveling a little bit slower than this photon that is at 780 nanometer or 781 nanometer wavelength. Like we can start segregating by wavelengths and actually get a little bit of time difference based off that dispersion. Now, time of flight has some very interesting applications for network security. They're already looking at this for formation flying of satellites, Grace and Grail, two satellites flying behind each other, and you get a very accurate knowledge of the different distance between them. You can kind of detect, you can calculate the gravity gradient of the moon or the Earth. Metrology, again, atmospheric conditions, the water vapor, the pressure, all those things change the time of flight between those photons flying between point A and point B. Network security, like I said, that's a big time of flight through a network. It's something we're pulling on with this DARPA discussion. And time difference of arrival. Time difference of arrival is essentially, triangulating the position of, say, a signal out in the middle of the woods. There's gunshot detection, things like that, that allow you to, if you have multiple sensors out there, you can use a time of flight to say, hey, there's where it's coming from. Oh, and the last one, I love this picture. This is the Wi-Fi, the dense pose from Wi-Fi thing, which is saying if you have a couple of different Wi-Fi routers, you can sense people in the room. Use AI and the subtle shifts in the time of flight to detect people in the room with you, including across on the other side of the wall. The other one too is this last mile PNT. So we attended this workshop, this NASA virtual workshop on kind of last 500-foot PNT, where this vision of autonomous air mobility, drones, self-driving vehicles, and so forth, where you're using beacons, potentially just 5G base stations, to create a local urban position and timing network. And one of the things that came out of that is the value and need of very tightly synchronized base stations, sub-nanosecond, but also having a resilient time backbone for that future. In some of the discussions we've had with groups that are looking at this, there's one word that typically isn't said within the timing community, which is safety. All of a sudden, that timing network you put in place has to be incredibly resilient, cannot be hijacked. No person can put in, time delays here and there, because that means loss of life. That means destruction of infrastructure. So this is something that could be very valuable for a resilient system like a quantum time transfer. Lunar and deep space missions, the NASA project that we got funded was a study phase to look at time distribution to the moon. Is very resilient to background, to losses, to link losses. So we could use this for time transfer. Not a big market for us, but hey, interesting. And then quantum networking. Quantum networking is the networking of quantum computers. It's called the quantum internet. My co-founder hates that term because it suggests that the internet where we have computers that are sending information between each other to servers. Networking quantum computers means you are entangling distant quantum computers. It means you are a 5,000 qubit quantum computer in San Francisco networked with a 4,000 qubit quantum computer in New York, has 9,000 qubits of processing capability. It's a whole other thing. Now, a lot of funding is coming down in the United States for quantum teleportation and quantum networking applications, but they all need very accurate synchronization because they're relying on quantum teleportation, which means photons are coming from two sources simultaneously to a third point, and they have to arrive there within picoseconds. So this is kind of driving the near-term opportunity for sub-nanosecond, picosecond level accuracy. A little bit about the hardware. This is a little video of our proof of concept, very basic, but that's the point. It consists of components that we bought very rapidly with small amount of funding, a source of entangled photons, detectors at Alice and Bob, and then a way to transmit them, an optical pointing and tracking mechanism, as well as the clock and processor that you want at Alice and Bob. And that's just, I think we use a rubidium clock at Alice and just a chip scale atomic clock at Bob, but we've also done it with oscillators. Now, the nice thing we're doing, like I said, we're leveraging hardware that was developed for QKD applications, including entangled photon sources. There's a number of companies that build them. We could kit this out and install this for terrestrial applications pretty much immediately. That video I showed you was what they call a spontaneous parametric down conversion type source, SPDC, shining a laser on nonlinear crystals. And there are groups that have launched this and are launching this on satellites. The picture on the lower right is out of Spectral, the group out of Singapore. They're launching this for QKD applications. And China's already got their third QKD satellite on orbit. So, yeah. And the other side is single photon detectors, FADs. Essentially like Geiger mode type APDs, where now you're measuring the individual click of a photon. The detectors have been developed for quantum networking and QKD applications. We're using those off the shelf, but we're also kind of looking at maybe a little bit better, a little bit lower dead time, a little bit lower jitter, better jitter time. So we're kind of looking at a little bit different parameters for a better quality, accurate time synchronization. And the lower part there, you're seeing very high efficient superconducting nanowire single photon detectors. So a lot of groups are working on this, but the key negative with those is they need to be cryo-cooled. So they're incredibly efficient, with very little jitter and basically no dead counts, low dot counts, I should say. And then the other technology we're leveraging is kind of, especially for space-based systems, is these pointing and tracking mechanisms, which have been developed for optical communication systems. 10 years ago, they were kind of a novelty on scientific mission. Pretty much any satellite constellation, including the Starlink constellation today, has optical intersatellite links. So they've gone from some exquisite to being off the shelf. And when we develop this, particularly when we're doing like terrestrial demonstrations, we can take this optical pointing tracking mechanism and we can separate Alice and Bob across, say, 5 kilometers or from satellite to ground. But for tests, terrestrial tests in the near term, we can have them side by side, have the clock side by side, and then bounce it off a retroreflector. We're just kind of, other groups have done this, but NIST has done this with their demonstrations of frequency comb and optical time transfer. So it makes it easier because you got the retroreflector up in the mountains and you just bounce it off that. This is all hardware, like I said, that we've already kind of built. We're looking to package it into something that we can stick into networks, something we can put on satellites, and something that we have portable so we can take it out and demonstrate it. I'm hoping we can go to a timing conference in the future and I can have it set up in a booth and, hey, just show everybody how it works. Particularly, illustrate the man-in-the-middle attack. Just the thing flashes red and it proves that we know there's somebody messing with your time signal. So our goal, one of the things we're working on, if we had the funds, we'd start building it tomorrow, is our satellite. Our first satellite we're going to launch is going to be a LEO compact CubeSat type design, where we're going to demonstrate Alice, synchronizing Alice on the satellite to Bob on the ground. Now there are issues or things where you got to overcome. It's not a trivial thing to get this to work. Having space qualified hardware is step one. Like I've shown you before, there are space qualified detectors and sources that have been built for QKD applications. The sources in particular have very careful alignment of the crystals with the lasers, and so you got to have a very stable. That's kind of the main challenge on orbit, because you got a wide range of thermal environments and of course if they go out of stable alignment, You can't send somebody up there to realign it. So that's one of the challenges with a source. Detectors, radiation effects actually degrade the performance of the detectors over time, but there's been some novel experiments being done on kind of laser annealing of those detectors to get them to bounce back. And then the other things you got to overcome are Doppler effects, point ahead angle, which breaks reciprocity for two-way time transfer. And then of course, just normal link budget type issues. So I think with that, I'll kind of wrap up here, give a few minutes to go to Q&A. I ran a bit longer than I expected, but again, just a little bit of background on our company. Again, this technology was invented by my co-founder in a paper in 2018, demonstrated in a quantum lab in Singapore, got 50 picosecond level accuracy, wrote another paper, patented it. We formed a company around this 2019. And we've gotten government projects, but now we're looking to develop this, put this on satellite and provide this for the network applications, for network timing applications that I mentioned, as well as those other applications. The IP is ours, but in the spirit of the Time Appliance project, we're trying to figure out a way to make this open source so that we can make this work with a wide range of users. That's a big mandate for working with Time Appliance project, and we agree with it. So we think we're not going to be IP patent trolls per se. We just want to work with and have our signal being used by a number of people. So it's for the benefit of everybody in the timing community. And one last but not least, highlight the fact that we're leveraging sovereign government quantum funding. The most advanced with quantum on satellites and quantum time transfer is China. Our original papers have been developed by China. They are responsible for roughly half of the global funding worldwide in quantum development. They've launched now their third quantum satellite. The US isn't even on this list. And I know plans to have it on this list. And like I said, they've started installing this. Okay, let me rephrase it. They've started demonstrating this across fiber, and they've started developing a national resilient timing architecture. So we're behind in these things. Again, I can give credit where credit's due, but with that, I guess I'll turn it over to questions.
Wonderful. Thank you very much, David. Okay, let's open the floor for questions. Any question, please unmute. And see. No one? Okay, maybe I can have the first one. So David, Jeff, you want to ask a question? Go ahead.
Yeah, I had a question. What if you partnered with the like AT&T in California? Could using their last mile, could you if there was a solution like that, would it work, or is that?
Absolutely. Yeah, so I'm glad you're teeing it up for me. This is great because we're at this stage now as a company where we want to install our system in test beds. We want to be able to show that this works on a kind of a warehouse out in the field environment. So absolutely, this is something we want to achieve out of this presentation, working with groups within the Time Appliance project. Launching a satellite will take a couple of years, just fundamentally, just if we had the money tomorrow, it's 24 months to get on orbit minimum. But there's a lot of things we can do to demonstrate and show this works in a terrestrial environment, in a network environment, that we're looking to leverage. So absolutely, I would love to, if you have some thoughts there, please reach out to me, david@zeros.com. Would love to explore that.
So in order to basically just deliver this in a elevator conversation, so you're bringing basically higher, let's say, security in delivering time or any other thing via quantum, like entanglement or you name it, right?
Absolutely, yes.
Yeah.
And it does have the accuracy. Again, we're sub-nanosecond, potentially better than that, better than kind of 10. Our goal as a company is a global timing network accurate to 10 picoseconds. So every point of the Earth synchronized to every other point within 10 picoseconds.
That's amazing. Yeah.
So this is what we're striving for.
So I have a question, and tell me which part of it is basically wrong. So imagine you're doing this quantum key distribution, and let's say you somehow can sample something from the stream of electrons, sorry, photons that you're getting on the two end, and let's say with that you get a key, and then the key is basically supposed to be the same thing. It's just distributed in two places. So now the frequency of these events, the keys, let's say let's say assuming is within, let's say, some sampling, and then the sampling will give you basically a time, let's say a time series. So now if you have, let's say, PTP, with PTP you are, let's say, within tens of nanoseconds. And let's say these the sampling of these let's say the time series is, let's say, within, let's say, 1 nanosecond. Would you be able to basically take packets, let's say take samples, let's say you take samples of, and let's say because you are within, let's say, 100 nanosecond, you take, let's say, a 200 nanosecond sample, and you ship it the other side, and the other side has been continuously, let's say, also taking like a circular buffer or something, and it aligns it on this, because they were all supposed to start with a start time that they got from PTP, but then they do the alignment with this, and they basically do a correlation. That correlation would show the difference, and then they can do correction. Is that what you guys are doing, or this is away from that, or?
No, I think Ahmad, you just created a new set of IP. I mean, so if I understand what you're saying correctly, so PTP is kind of the protocol where you're using kind of packets, or I guess the signals to as a way to kind of do the.
Basically, I'm going coarse and then going fine.
Yeah. So, but fundamentally, put aside the PTP. Fundamentally, we're just, like you said, we're creating this random, sequence of photons that are measured at A, and it's sent over to B. Not all those photons make it from A to B. Like, a lot of them get
lost. That's why
along
the correlation. It's statistical still, right?
Yep. So that's 100% what our protocol does. Is just A. I'm measuring it at A. I'm measuring it at B. And then that cross correlation tells me the offset and synchronization between the two clocks at A and B.
Would this service you have be able to support that?
Yeah, again, the devil's in the details. So yes, I will say yes, but I got to confer with my team to see if I'm.
No, I mean, I'm not saying I want to pay. No, I'm just saying theoretic, because I see that you have a key that goes everywhere, which comes from the same source. So that's a key distribution. So if I have a key distribution, but I mean, there is and I'm aware of like the, devil's in details. Like I want to sample that, great. Let's say 1 nano, I have to sample in 1 gigahertz. That's fine. But if I want to go further, it just gets crazier and crazier. And then you have to store all of that. And like, I mean, it's not impossible, but I mean, devil is in details, right?
Yes.
But I was just thinking, like, okay, if you have this piping, then you can put whatever you want, right? You can put this precise sync. I mean, still you need the holdover. Still you need like. I think Nobu is here. He left. Yeah, Nobu. And
I was looking for. Oh, there he is. Shigesan, good to see you.
Yeah. So yeah, like I mean, it is kind of similar with how YY does it, but now you're doing it with quantum, basically. Like everywhere we go with the MDT is like it's just showing up. It is somehow similar to that.
Yes.
So can I ask one question?
Yes, good.
Yeah. So I guess you have already done the proof of concept, and that proof of concept is mainly to sort of exchange the sort of timing signal. And I guess you haven't connected that to the flywheel and then sort of evaluate the clock, sort of the clock synchronization? I mean, like what I'm saying is, did you measure the time error versus time kind of plot? Is what I was curious about.
We're working on that right now, so that's a great question. So part of our next step is proof concept. We basically stopped short of actually kind of getting that calibration between. So like the flywheel, I think what you're saying here, Shiga-san, is we're using kind of the relative clock sources at Alice and Bob to kind of figure out the relative offset between them instead of the absolute offset. You got to kind of connect and do that extra step to say, this clock is running at this time, this clock is running at that time. Step to synchronize Bob's clock to Alice's clock. Now, part of what's holding us back there a little bit too is just, we're really kind of focusing on optimizing the algorithm right now. And also, kind of that calibration step, which requires fairly advanced hardware that we need to, potentially we can go in and use NIST facilities. I'd love to be able to use NICT facilities, quite frankly. That'd be outstanding. So, but again, so then we can kind of connect that final step, which is say, clock A, clock B. Here's the absolute offset that we need to correct for. So I think that's your question. Maybe I'm missing.
Yeah. That would be really great. And another question, I have another question that is, if you are using sort of quantum key distribution type of algorithm, like in the slide you mentioned that you need the classical authenticated classical channel. And are you planning to do that as well through the satellite with photons, or are you going to use other channel between two sites?
Yeah, I mean, we could just use the RF link between the satellite and ground, but what we want to do is put an optical comm link, mux it in with that. I mean, we're already establishing the optical link between satellite and ground. So essentially you got a source detector on the satellite in addition to, a modem and EDFA on the satellite that provides the optical communications. I kind of ran out of time because I glossed over a little bit, but you also need...
Time is abundant in TAP.
I love it. Yeah. No. So on the ground, you want to have a lot of the same elements that you have, or on the satellite ground, you want the same elements that you have for optical communications, including a beacon. So you have an uplink beacon, satellite comes over the horizon, and it has a rough idea where to point, and then it picks up that beacon. That beacon, for all intents and purposes, can be that optical communication link. I mean, and then, again, you got that one established link. You're confident there's no disturbance of that because, again, you've got the exchange of photons and you can verify that. So, you got all in one, system right there with that one link. So, yeah.
Oh, very great. Thank you.
Awesome. Any other question? Maybe one more question, David. Would there be, again, this is like something I receive also like from this entanglement per se, the theoretic entanglement that you have two particles that are entangled, you separate them, you take this away, and then like you have the entanglement established, which we don't have. We have it all like with the optic link basically. So with that, let's say if that happens, would that ever make this different? How are you doing this, or like any of that sort?
So great question, because we're following along on these developments on what they call quantum networking. I kind of hinted at it before, which is this idea that you can entangle quantum computers. And fundamentally, what you need for that to work is you need quantum repeaters, essentially a way to move the photons, the entanglement, and have it stored and repeated, or recreated or stored and like repeated, sent along the way, I should say, as well as quantum memories, which will store.
Quantum memories.
Yeah. And so I'm explaining it badly, but that's the gist of what is being developed with quantum networking applications. Now, I have seen, there have been papers that have been released. I think it was a group out of Oxford that showed some of these methods for entangling these optical lattice clocks. Very impressive stuff, but we are a long ways from having the capability of entangling them over long distances.
Yes.
So I think everything you're saying about is in theory, yes, but just technology breakthrough wise, it's a long ways away.
Yes.
One thing what's that?
If possible, yeah.
I'll let the quantum physicists hash that out, but it's definitely the quantum networking thing is getting a lot of funding and a lot of interest in the United States. And there are groups that are slowly working on it, making breakthroughs. I know I kind of sit with my co-founder and other scientists that we're working with that are at the forefront of this. And, it's a matter of kind of making those kind of technology leaps.
Absolutely.
For anybody who's familiar with quantum computers, it's crazy impressive what they've been able to achieve. So,
absolutely. Yeah. So we have a question from Oliver. Oliver, do you want to ask or you want me to repeat it? Giving Oliver 2 seconds. I guess Oliver delegated me to ask. So Oliver is asking, I understand, I don't understand, where is the timescale transfer from an official meteorological source, NMI, like what's basically the meteorological source? And for me, I understand that is a phase synchronization between samples, no time synchronization in real time as is in PTP or White Rabbit.
So and again, I'm just trying to make sure I understand the question correctly. So we are engaging with NIST. We've had some engagements with NICT and groups like that to kind of help us kind of with the calibration aspect of it. The absolute time transfer, yeah, that's something that we're working on as we speak. We just haven't, it's kind of, like I said, we're focusing more on the optimization piece for getting to the absolute time transfer piece. Nothing says that it's kind of a technology
can accept
a challenge. It's just it's just a step we need to do in there.
Yeah.
So
this is what you put in basically. Anything can be placed in here. Yeah. Any more questions before I call names one by one? Dan, Hisham, Akira, like Steve, Jeff already asked his questions, so okay, hearing none. So again, thank you again, David, for the presentation. Great presentation. I love this quantum stuff. And so presentation, as usual, again, is recorded with the slides available on the wiki. And also next week, sorry, not in 2 weeks, next OCP tab session 78, we'll have Judah Levine talking about digital, what was it? Let me see the title. Digital time services. So, okay, great. Jeff, do you have any question or we good?
No, I was just saying hi before I left.
Awesome, wonderful. Great. Okay, then see you guys in 2 weeks.
Oliver have
Bye,
some.
everyone.
Thanks, David. Thanks, Ahmad.